This is Asterios from TU Delft, and today I want to talk about basically how to program general cloud applications and whether Dataflow engines can be the perfect fit for those. What will we cover, basically? I will first show you how people build scalable cloud applications today. What's the state of the art, let's say. What are the main pain points when people are trying to develop such cloud applications? Whether it is a good idea to leverage Dataflow processors for general cloud applications, like the ones I will show you in a bit, and whether, if that is possible even, whether the current Dataflow processors are up to the task. And finally, whether the PL community can help. I'm a database person. I also do a lot of distributed systems things. I do believe that success lies in the intersection of the three: database, systems, programming languages, and distributed systems. We'll see about it a bit later. Now, a very brief note here. When I talk about Dataflow processors, I'm talking about streaming Dataflow processors, meaning a system which is going to be parallel, right? And it's going to consume streams and process them on the fly. So that's what I mean by a Dataflow processor. Think of any streaming system like Apache Flink, Hazelcast, Jet, Spark Streaming, any of these, we will call it Dataflow processor. Good. So let's start. I will base the whole talk on three very basic services that one wants to build in the cloud. Those happen to be, let's say, textbook examples that people use a lot. And people use them a lot because if you have these triplet of services, there's so many problems you can describe around them that they make a fantastic example to be used in textbooks and presentations. So this is basically the shopping cart service. The shopping cart service is the service that holds your shopping cart. It says which items and how many of those you want to buy from an e-shop. The payment service is a service that you give it an amount, right? And then it charges a credit card or a bank account. And the stock service, or you can also call it inventory, is basically a service that keeps account of how many items you have of each category. For example, I have 10 pens and 5 cameras. Good. Now, the goal here is to design a system that at cart checkout, it will have to update the stock, right? It will have to basically decrement all of the stocks that you just bought from your shopping cart. It has to verify the payment and make the payment. And what's very crucial here is that the stock should not be updated unless there's a payment done. And you should not get paid unless there was stock available and you decremented to reserve it for that specific user. So that, in classic database terminology, is called an atomic transaction. You will either do everything or nothing at all. You cannot be paid unless you check out the shopping cart. You cannot check out the shopping cart unless you have paid and you have updated all of your items. Now, how do people do it nowadays? Historical reasons have led to the following approach. You have two layers, what we call the service layer, which is stateless. This contains the business logic of all of these services. And you also have the database layer, or the stateful layer, which is, in the best case, a database which is being given to you as a service. So you rent a database from the cloud, somebody gives you an endpoint, whatever you're running at the business logic runs without having to care about state, and all of the actual state updates happen in the database layer. So let's see how we will build this with the current systems of today. Normally, if you put basically a master student to do something like this, they will implement the following thing. I have tried, that's why I know. they will implement the business logic in something like Spring Boot or Python Flask or Akka Actors, right? All of the business logic will be there. They will assume some database to be ready to do the work, either by a cloud provider or a database admin or whatever other victim they will find to do the hard work. The services between them, they will exchange REST calls, so HTTP calls basically, and access to the state, the current count of every item, the money, etc., is going to happen with RPC calls between the business logic part and the database. Now, this is extremely easy to program, if you ask me. If you put any master or even bachelor student to do that, they will do it. And it's not going to take a long time for them to do it. But it has some problems. The first is that you have to assume that the database is there for you. Unless the database is there for you, given to you, you have to do all the state management yourself. We'll talk about this problem a bit later. There is a very high latency because every time you need to access the database, you need to pay for those RPC calls, right? There is no guaranteed messaging, which means that these REST calls that you see here, if the stock service is down, whenever you ask the stock service to update the items, you may get a response or you may not get a response. If you are lucky and the stock service is up and running fast, you're going to get a response. If not, you will have to implement within your business code a piece of code that will do the following. It will check whether the stock service is alive, if it's alive, if it's fast enough, and if it's none of the two, it will keep retrying until something good happens. Now, you can very easily see that in order to implement atomicity here, things get very, very dirty, right? Because all of the updates of the stock service are going to happen at some point. Maybe you update the stock and then you never get paid and you have to return the stock back. In the meantime, somebody else may have tried to basically buy from that item, but there was no stock available. Exactly the same happened with the payment. You may make the payment for stock which is not there, etc., etc. So people solve this problem in two main ways. The first way is to perform two-phase commit. You remember it from the database class, I guess. There is a bunch of standards out there. One of them is the Java XA, which is something very old that some of you may remember if you're old enough. It's still being used today. Or you're going to use sagas. Now, sagas is a form of transaction which is eventually consistent. So you're going to take the stock, you're going to make the payment, and if anything goes wrong, you're going to send compensating actions to the services to take back what you did before. For example, in the payment, you will give back the money to the client. In the stock, you will put back the count of the items inside the database. Now, the consistency of this system is going to be very bad because it's up to the programmer. And whenever people tried that since the 70s and up until today, it didn't go so well. Now, let's make this service a bit faster. Let's say that we will take the database and put it inside let's say, the container in the cloud that is running the business logic. What is the result there? It's that database access is going to be much faster. And the problem that we introduce in this case is that the fault tolerance is going to be very hard. Why is that? Because before, the database was being given to you as a service. At this stage, the database is your own responsibility. So if something fails, for example, in the shopping cart service, you will have to somewhat find the state that you have lost and put it back in before you can spawn new services. Right? The second problem that we have here is that it is not very obvious how to scale this out. So if I want to have two different instances of the shopping cart service or the stock service, I will have to shard the database. So half, let's say, of the users of the platform will have to go to one service and the other one to another. Again, this has to take place by hand, essentially. Now, let's try to fix the fault tolerance part, and we'll talk about the service, about the speed a bit later and the safety. Fault tolerance. Let's fix fault tolerance. If instead of doing REST calls, you replace the REST calls with what we call an event log, right, or a message broker, depends on what background you come from. Basically, all of the exchanges between the services are going to go through the event log. If the event log is a persistent event log, which means whatever you push inside, and no matter whether there are failures happening in the cloud or infrastructure, you're going to have that event received by the receiving service. So if that happens, the event log is going to do the work for you. So what have we fixed now? In the case of the services here, whenever you push a message to the event log, you are sure that eventually it's going to reach the target service. Now, this is very important. Why is it very important? Because once you get a hold of the event log, you no longer have to keep trying and retrying and checking if the stock service is still alive or whatever. Whenever the stock service goes back up, it will read the event log, it will receive your message, and it will push similarly something in, which is also going to reach you, right? So now we have achieved what we called at least once delivery. Okay? At least once delivery means that if you send a message from one service to another, that message is going to be delivered at least once. In the previous case that we had with the REST calls, we would call that at most once delivery, which means you send a message, but you never know when or if it has reached the target service. The problem with at most once delivery is that all of the error checking has to take place in your application code. Now, the problem with at least once delivery is duplicate. You may receive a message at least once, which is from 1 to infinity. Let's say you receive the message 5 times. In that case, what you need to take care is what we call idempotency. Basically, for the same message that was sent by the card to update the stock, if you receive it twice, you should basically ignore the second one and keep only the first instance of the message that has reached you. Right? Good. So, result with this architecture. We have basically eliminated the latency to the database. We have achieved at least once delivery of messages, which makes our business logic much nicer. And very important, if something fails, if this database goes down in a minute from now, all I have to do is go to the message to the event log and rerun all the messages that somebody sent me since the beginning of time, and that will enable me to rebuild my state, right? If I was, let's say, the payment service, I will simply initialize my state to be 0, and then I will read all the messages with money coming in and out of my bank account. And eventually, after I consume all the event log, I will end up with the correct state. So, long story short, this is going to be fast, and this is going to be fault tolerant, and this is going to look relatively nice on the business logic side. Good. So the only thing that's left now is to scale this out. Let's try to scale this out. If you want to scale this out, you're going to end up with multiple instances of each service. In the case of the shopping cart, you see here that I have basically sharded the database into 3 parts. And I have 3 instances of the shopping cart. The users in my platform, they're going to be hitting one of the 3 shopping carts at any given moment. So now I'm suddenly 3 times more scalable than before. Exactly the same will happen with the stock, and exactly the same will happen with the payment. We left the payment, let's say, with just one instance here. Now, we inherit all of the nice properties of the previous architecture, right? And in addition, we scale well. So at this stage, let's say the chief architect of the company would be very happy because we have a scalable shopping cart that doesn't lose data, and whatever happens, it's going to recover from failures. Good. Now, let's keep this, just keep this picture, this architectural picture for later. I, in fact, make my master students implement this every year. What this thing is almost, for master students at least, an impossible task. So we basically allow them to use any tech that they want to in order to implement the shopping cart service, the item, the inventory service, and the payment service. And they're allowed to use Amazon Lambdas, Flask, Akka, Spring, CockroachDB, DynamoDB, Kubernetes, and whatever they want. And at the same time, they are also allowed to use whatever cloud resources they have, up to a reasonable limit, of course. Now, the class runs for the last 4 years. And basically, I would like to ask you how many student teams you think made it so far to execute around 10,000 transactions per second with whatever resources they wanted, without losing money and without losing items. Any bets on the live or online?
Less than half.
Less than half. Who was that, by the way?
Diagno.
Yeah.
From VUB, Universiteit Brussels.
So I heard less than half. I will break the news to you. It's been none so far. Okay. Now there's a bunch of things you can think about it. You can simply say Asterios sucks in teaching. That's a valid assumption to be made. You can also think that the task is impossible. Yes. It's just 3 services. The answer I have come to conclude, basically, is that simply the current technology is extremely primitive. And this is stuff that very, very few people in the world can do correctly. And I mean correctly. You cannot lose an item. You cannot use $1. It sounds easy, but it's not. So let's see. This is the actual, what you see on the left, basically, is the actual code that the students, one of the good student teams have given us. This was in, if I'm not mistaken, Python Flask. This is not only, this is just the business logic, let's say, that they wanted plus failure management. What do I mean by failure management? They always had to check if, for example, one of the services that they were talking to was down. They had to implement idempotency, what I told you before, that if you receive a message twice or a call twice, you should only act upon the first one. They had to ensure atomicity. They had to ensure consistency. They had to recover from failures because we are killing randomly machines while their service is running. Fault tolerance, parallelization, auto-scaling to achieve the 10,000 transactions per second. What I marked here with green, in fact, I could even zoom into this. This is the actual code. This is the useful application logic code. What do I mean by that? When you have, for instance, you have to first check if there is enough stock. And if there is enough stock, you can basically decrement that stock. And you also have to check if there is enough money. And then you need a bit of glue code to basically make sure that everything clicks before you check out the cart and you reinitialize it so that the user can do something more. Which, if you think about it, it wouldn't be so long if you would write it for a centralized application that doesn't have all of these issues around it. Now, long story short, why is this problematic? This is problematic because in order for the students to get to that program, they need to understand very well what we call serializability and transaction processing database systems. In fact, they have to code transactions in application code. They have to know about distributed systems, failures, cloud computing, and all of the things that come with it, checkpointing, messaging, exactly once processing, and all of these concepts. And of course, yeah, don't forget the domain knowledge that you need to have to make the shopping cart, which is trivial in this case, and of course, programming skills. The problem with all those is that the right person to develop such a service lies in the intersection of those. And I have met so far very, very few people that are experts in all of these. I don't count myself either. Long story short, if we want people to develop nowadays scalable and consistent cloud applications, they have to have all of these. In fact, if you want them to have all of these, they are going to be extremely expensive to hire. In fact, in academia, we wouldn't even have a chance to hire such people. And in the end, yeah, they are going to be joining the Googles and the Amazons of the world. So what do we do? If you think about it, any attempt to develop a general cloud application which is scalable and consistent nowadays is reminiscent of basically what we were doing, I don't know, with assembly programming before the compilers were around, right? And high-level languages. This is exactly the same situation that we have here. We have 1 trillion abstractions. People have to learn by heart all of the abstractions of every different cloud provider and then hard code everything themselves. So the code that I showed you here is mostly failure management. What happens when either a service is very slow or it does not respond, right? Or it has responded to my first request, but not the second one, etc., etc. So basically, the code is littered by cloud failures or distributed system failures. So the question basically we are asking now in Delft is the following. Can we hide those failures from the programmers? Right? Let's just see if we can hide those failures from programmers. And if we can, to what degree can we hide those failures? Now, before we start, there is an impossibility in distributed systems. And if you remember the two generals problem, basically it tells you something very simple. That if you have two generals, that they are using a messenger, right, to cross the valley and go back to the mountain to the other general, and if the generals want to agree on what time to attack the city, which you see here, they have to send a messenger. The first general says, do you want that we attack at 5 o'clock? The messenger goes to the second general. The second general agrees. Yes, let's attack at 5 o'clock. And then the messenger again goes back to the first general and reports. And if they agree, they will attack the city. The problem with that is that the messenger can be killed anytime because the messenger is a human and they have to cross the valley and up the mountain until they get from one general to the other. Now, the possibility of the two generals problem basically is that the last general to send a message is never sure on whether the receiving general has received the message. Let's say this general sends to the second one, let's attack at 5. The messenger will go to the second one will agree, and the second one will send the messenger back to the original general. Now, the last one to send, this one, does not know, right, if the message has ever been received by the original messenger, which means he will not go to attack the city because he's not sure that the other general is going to be in the city either, right? So this is an impossibility that's probably impossible, basically, with an unreliable medium to achieve any type of consensus between two generals. If you translate it to our case, it tells you that two cloud services cannot check out the shopping cart if they are using unreliable cloud machines or network. Now, before we surrender completely, let's discuss a couple of things. Let's suppose that you have the set of all cloud applications that we can ever program. In the general case, simply because of the too generous problem. It is impossible to hide the failures from the programmer due to Byzantine generous problem. So basically, we solve most of the problems nowadays in distributed systems, not with smartness, neither technology, but with business logic. What do I mean by that? If you take the money of a client and finally the item was not there, you will simply send them 5 minutes later an email saying, actually, you checked out your shopping cart, but there was no stock. I'm sorry. So most of the problems, we solve them with actual business logic and things that people come up with in business. Except for a very small subset of cases that with two-phase commit, we can basically do the following. What do we do there? We do not allow the state to be visible unless we have received all the answers from all the generals, right? So in some way, there is, think about it as follows, there is a set of specific cases that we can reach an agreement under certain assumptions. Now, if you think about it in the context of, for example, Dataflow systems and streaming systems, when you are developing a streaming system and you say, I don't know, map and filter, and this is deployed in the cloud, nowadays, we can hide all the failures from the programmers. We do not hide them from the ops team, the operators team, but we can hide it from the programmers. The person that writes the function, that's the map function or the filter function or the join function in a scalable stream processor nowadays, in a streaming data flow graph, they do not need to take care of anything there. Good. So, long story short, in certain cases, it is possible to hide all the failures from the programmers. Now, this holds for Dataflow applications. What do Dataflow applications run? Database queries, you think of stream processing queries, big data analytics, ML pipelines, and whatever basically you can represent as a data flow graph or a directed acyclic graph. Let's see if we can basically extend this a bit to what we call transactional applications, okay? Like the one of the shopping cart. What are transactional data flow applications? Think of shopping cart applications, very complex transactional workflows, fraud detection systems, supply chain systems, etc., etc. So those we will call transactional data flows. So the important thing that I want you to remember from this is that unless a system, okay, and now I'm talking about stream processors of nowadays. Let's take the example of Apache Flink. Unless a system combines the state, the business logic, and the messaging, exactly one's processing of those messages is impossible, right? We will see exactly how that works in 2 minutes. But keep that in mind. Exactly once is impossible. We don't know any other way to do it nowadays unless we combine state, logic, and messaging inside the same execution engine. In this case, let's take the example of a streaming data flow processor. Now, unless we guarantee exactly one's processing of messages, the failures will eventually leak to the programming model. So the programmers will have to deal with the failures. What do I say? Why do I say this? Imagine that I want to update the shopping, the items in my inventory, in my eShop. If I send a message to the inventory service and that message has no guarantee of being delivered, I will have to work around it with business logic. I will have to hard code transactions in my application code. If somebody tells me though, that just tell me what the item update will be, and I, as a system, as a, let's say, execution system, I will guarantee to you that that message you send to the inventory service is going to be delivered and it's going to be processed exactly 1 time. Then I never have to worry about the failures that will happen in the system, no matter what happens. Are we all following it's an important aspect now here. Or any questions? Does anyone want to make a comment to this stage? I will assume no. Good. Since we understood everything, let's move on. Now, let's see what we can do about it. Okay. Remember what I showed you before. This is basically multiple instances of the services that we have, connected via event logs. The state has been sharded to multiple instances, right? And there are messages exchanged between services via event logs. Now, if you take a deeper look at it, and you also look at what the streaming processor does today, they are the same thing. If you write, for example, a word count application in a stream processor nowadays, or a join and a filter on a stream processor, this is exactly what the stream processor will do for you. It will shard the state, it will make sure that the connections are on, and it will guarantee for you exactly once processing of all the messages that these operators are sending between them. Let's take a look a bit deeper. If you take any of the existing stream processors nowadays, take Samza or Flink or Jet or Kafka, anything, they basically all, by now, and since, let's say, 3-4 years, they can all guarantee for you the following: that message delivery will be done with exactly once processing guarantees, okay? That every operator can execute a business logic in whatever you give it to it, that the state of that operator, let's say an aggregate or a window, is going to be local to the operator that needs it and also sharded. And whatever happens to the state, it's going to return back to its original state, right? And with this come some very nice properties, like, for instance, time travel debugging using the checkpoints and the message queues that have been sent. Basically, what you do there, if something happened last night in your Dataflow processor and there was a bug, you can simply take all of the messages, replay them in front of you, and then debug what happened last night. So all of these will be given to you for free. Now, where is this going? You might be wondering. The Dataflow systems of today basically suffer from a bunch of things. Let's ask the question: can we use Dataflow processors as the execution engine for general cloud applications, right? And eliminate all of the failures and the failure management from the application code of programmers nowadays? You will hit some problems. The first is that failures will require the redeployment of the complete graph. If you want to ensure exactly once processing nowadays, you do have to redeploy the complete graph. The internal state of the stream processors is not queryable just like a database. For instance, if you would have the database as we had it in the previous example of the services, you would simply query how many items do I have left in my system at the moment. The most important thing, and why I'm here today, is that the programming model sucks for 99% of the people. We may love functional programming. We may love Dataflow programming, but for 99% of the people, this is not what they want to spend their days doing. They want to write normal imperative code. And finally, stream processors nowadays do not support transactions. So let's tackle the first issue first. Failures. How does this work? And maybe I will run out of time, so I'm going to take this a bit fast. So this is a stream processor. Every entry to the system is going to enter through an event queue or a broker, whatever you want to call this. This is what we see here on the left. You will have basically operators or services that we have in this case that exchange messages. Messages can be either payload, for instance, an event that goes from one to the other to make an aggregate, or it can be a control event, right? Now, every now and then, the stream processor will take a checkpoint, right? And this checkpoint will be used later together with the input queues that we have here to replace some messages and return to where the stream processor left off before it failed. So let's see how this happens. Let's say service 4 dies. What will happen in this case? We are going to delete completely the whole data flow graph. Then we are going to set up the services back in. We are going to set up the connections between the services to be just like it was before the failure happened. And then we are going to take the state from our checkpoint store. In this case, it could be Amazon S3 or HDFS. We are going to return the state to the operators. And then we are going to replay some part of the queues in order to get basically the computation back to where it was before the failure happened. And this is what we have to pay to achieve what we call exactly once processing. Stream processors nowadays, no matter what happens, failures-wise, they are going to guarantee to you that the message is going to be reflected in the state exactly 1 time. Good. The problem is that this whole failure protocol I described now is quite slow, okay? And it will take a lot of time. So if we are to use a Dataflow processor for general cloud applications and high availability, very, very fast, you will see that a traditional Dataflow processor will not do the job. Simply because if a failure happens, it will take you like 30 seconds to return. And that's 30 seconds too late for any normal application you will have on the web. So can we do exactly once and at the same time recover much faster? I will not get into the details of the protocol, but what we have come up with basically is a protocol that uses causal logging, and it basically makes sure that exactly once processing happens, also with local recovery. This means that instead of waiting, what we have here, instead of waiting around, I don't know, what is that, around 60, 70 seconds for the system to come back to normal, you can basically recover within 3 seconds. Flink is what we have used to implement our system on, and Clonos is the approach basically that we have developed here. What I wanted to tell you with this is the following. Dataflow systems today suffer from long recovery times, but this no longer has to be the case. Okay, so let's move on a bit and see other problems that you might have with Dataflow processors. The second problem that you will have, which is basically closest to the PL community that we are here today, is that the Dataflow programming model sucks. And I'm sorry if I don't know, if somebody feels uncomfortable with what I'm saying. I'm just talking about what people tell me. Okay, people I talk to do not like functional programming, and they hate Dataflow programming. Okay, if anyone wants to debate this, I'm very happy to debate it. A lot of the people I talk also suffer from actor phobia, let's call it, for a very, very simple reason. They love the programming model, but they don't like the at least once processing semantics. They do not like that, again, just like we do with normal services, they don't like that they have to implement in application code, within the actor code, retries of sending messages and sometimes making sure that things are redeployed. So the question that comes to me is the following. Can we use imperative programming? Because people love it. All schools teach it, and it's very easy to find programmers that know it. Can we use imperative programming and still inherit all of the good things that come from Dataflow systems? This would basically entail the following thing, that I will take an imperative program and I will try to rewrite it such that it forms a data flow, and then try to execute that data flow on the execution engine that runs data flows. So let's see how this experiment goes. On the left, what you see is object-oriented Python code. with a couple of twists. The first twist is that every what we call entity, you can also call it an object, you can also call it an actor. These are the same thing. We call it entity in this case because we don't want people to think of actors when we talk to them about this. For very pragmatic reasons. You can call it an actor. So in this entity, which is basically the user, and you also have the item, what happens here? You have a user that has a transactional function call called buy item. You will find basically how many items of what amount you're going to buy. So how many items? Let's say 5 items. Of what price? Let's say $3 each. It will give you $15 in the total price. If your balance is smaller than the total price, simply declare that you cannot buy it. So return false. But if everything goes well, continue. Go and item update the stock. For every item basically in there, just update the stock. Where is update stock? Right here in the entity called item. And then if there is no available stock, give the stock back and return false. But if everything goes well, again, simply remove the total price from your balance and return true. Okay, you don't see it here. Good. Let me show you now how this will run in the Dataflow graph. Now, the question basically that we have here is the following. Can I take this code, compile it, extract from it functions, and then rewrite them such that they form a Dataflow graph, right? Let's see how this can work. The following thing will happen. You will have the user here and the item here. Again, it's the same code, I just replotted it in a very different way. So what happens here is that the first part of the program is going to do the following. You will execute the buy item function. And when the time comes that you need to access somebody else's function, right, you will have to stop your execution right here, just before the yellow part starts. You will have to stop your execution here, right, and go execute this remote call. Again, if you are running in a Dataflow engine, this remote call is going to be on some other operator running possibly remotely, and most probably. So you will stop here, go and execute that price. The price will return the value. And then again, with an event that travels through the Dataflow graph, you're going to receive an answer to your call, and you are ready to start the yellow part, right? The yellow part will execute as long as there is no need to call any external function, right? And once we get again to item update stock, we will have to leave this operator, travel through the Dataflow graph, execute this remote function, take the return value from that one, insert it to the new function, and continue from there. Now, you will very quickly see that this is, to some people, it reminds them of CPS, continuation passing style, because this is exactly what we do here. There's nothing magic, and I think for most of you, no news here. What is news here? The following is what we consider to be new. Whenever you do this, you simply have to pack all of the state, basically, from the previous function. And all of the local state that is required through Dataflow analysis to the next function that you're going to execute upon execution of the remote function in order to return and be able to continue the execution from where you left off. The magic thing about this is that if you do all this, you can basically compile this program into a Dataflow graph where pure functions basically are going to be translated from the imperative style into continuation passing style. And you can add those as functions in a Dataflow operator. You see here, for example, we have by item 1, 2, 3, 4, 5, which is exactly what we had previously here. So here we have this answer. Long story short, you can take imperative code, of course, with some conventions, Okay, you cannot do that, I don't know, for whatever code you have in front of you. You can take imperative code, transform it to continuation passing style, and then transform that one into a data flow graph, and then hand it over to a data flow processor. You can simply take this and give it to Flink. Flink will happily execute it. Now, what did you achieve if you do this? You achieved exactly once processing. Because suddenly, you do not need to worry about failures. If you see here, what we have here, there is 0 lines of code that have to do with failures. 0. And how did we manage to do this? Simply because we are leveraging the data flow graph and the data flow engine that is executing this whole application. And in fact, I think I forgot to add the performance measurements here. This is an experiment we have done, basically, and we are going to talk about it in Cider 2023. And we have basically managed to have a compiler which is less than 4,000 lines of code for Python using metaprogramming. We execute on Apache Flink, and we indeed can have provably exactly once processing. And what you see here is exactly all the things you need to write in order to have an imperative program compiled into data flows and running as distributed services in a scalable fashion. Good. The result basically is that from what we have seen previously, that 95% of the code was failure management, we got to this stage, which is basically normal code, whatever you would write if your code were to run locally, with some annotations, which we call this 90% useful code percentage. Good. Now are we done, is the question. The answer is no. We are far from being able to do all these. This was an experiment we have done basically at Delft, and we continue working on it with Guido Salvaneschi also taking part in this effort. There's a bunch of things to be solved before we can take data flow processors and use them as execution engines for general cloud applications. We are currently working on transactions and developing our own data flow system at the moment that will execute transactions. And we are also working on auto-scaling, migration, etc. Meaning, if you deploy a data flow processor in the cloud, it will be able to self-adapt to the workload, scale down or scale up whenever it needs to, and all of this while trying to retain exactly once processing, because this is what basically enables all of these good things to happen. So, my claim today is the data flow engines can become a universal execution engine for scalable and consistent cloud applications. That includes batch processing, like databases, stream processing, because this is exactly what stream processors were designed for in the past, ML workloads, and even transactional workloads. What we need to fix on our way there is that we need to make data flow processors programmable by normal folks, and that means we need to forget about the data flow programming model and give people imperative programs and models to develop on. So that's all I wanted to say today. I hope it was not very heavy, and I'm very happy to discuss.
There's people with questions I can pass around.
Hi, can you hear me?
Yes, I can hear you.
Okay, perfect. So I was wondering, the sequential code that you showed with these entity annotations, it reminded me very much of some work that has been done in TLS and choreographic programming, where you basically start with a sequential program and then you slice that program into several components and compile different programs for different machines, and then you basically synthesize all the communication code. So how do you think that compares to your solution, and where do you see the role of these languages?
Excellent point. I don't know what choreographic programming is, and to my surprise, it's the first time I hear about it. I don't know what is the difference there. What I suspect the difference is that I would be almost sure that the engine running those programs would not be able to guarantee to you exactly one's processing. This is just a claim, though. Can you send me an email, please, and point me to the right place? I would be very, very interested to see what happened there.
Yeah, maybe Pascal can also elaborate a little bit on that, because I know that he has done some work on TLS programming.
True. Yes. Yeah, I did. So it's a bit of a different domain, I would say. So it's usually about network application where parts run on a server, some maybe on your smartphone and so on. And the idea there is that you can kind of develop your complete system in one compilation unit, and then the compiler takes care of distributing the components to the different devices, and then adds like the network communication code automatically for them. So I guess in that sense there are some similarities in the way that there is some splitting going on for the different parts of it. I think you're kind of right with the one delivery guarantee that's not usually a part, at least in choreographic multi-programming.
And do you have to include failure management code in those functions? Is it something you have to worry about?
It's something you worry about. It's often something that it's not like automatically guaranteed, I would say. So you often get some abstractions that help you discover when some node goes offline, and then you can react to it.
Okay. Yes.
But how you react to it then is very domain specific for the application, right? So it's hard to automate in that case.
Yes. If anybody can point me to that, that's why I came here.
Absolutely. Yeah. Are there further questions on site or remotely? Otherwise, this question. Okay.
But I'll go ahead. Okay, I'll ask my question then. In the imperative code you showed, I think that there are some. Let me restart. Are there any requirements of the imperative code? Like, for example, I saw an update stock method, which imperatively updates a stateful variable. But what if I directly access that variable myself, for example, in the code here on the left? Then there might be some inconsistencies or glitches. Like, can you elaborate?
Excellent. Yes, you got me. Exactly. So in this, let me tell you the assumptions that we have, that we are working with at the moment. First of all, every entity needs a key. Why does it need a key? It needs a key because whenever I need to basically call that entity and the function on that entity, I need to find where that entity is. So first thing, every entity needs a key. So unless you implement the key function, the compiler will complain. The second thing is that you cannot access directly anybody's state. Hands off. If you want to attach anybody's state, you need to call a function on that entity, and that entity should take care of that. The third thing is that by, let's say, by convention, everything that you declare as an attribute on the object, in this case, for example, you have the username and the balance, or in this case, you have the stock and the price. All of that is going to be considered checkpointable state that the system, the Dataflow system, is going to checkpoint for you without asking. Now, problems become, as you can see, very fast. You can very fast develop something that's going to look very ugly. What do I mean by that? We do not allow recursion. Okay, you cannot call yourself. And where do things get ugly? If you have, let's say, very big local state in your function, I don't know, you want a video to be next to your item stock or something, then this will be checkpointed, and this is going to be slow. So these are the main assumptions, but you are right. In this case, simply by convention, we have to restrict the language from, basically, Python allows you to do anything, by the way. I don't know if you are familiar with Python. Python is hell. We need to make those basically assumptions. Yes, that most of them we can detect at compilation time. We are not sure if we can do everything. Again, we are not PL experts. We're database people. Excellent point.
I have a question, which is, firstly, thank you for the talk. It was really interesting. I built a little reactive event sourcing database in the summer after my undergraduate, so it brought back some fun memories seeing that. My question is on lowering imperative code to a Dataflow graph program. I was wondering if you had looked into, a few years ago, there was a PhD thesis and some research papers around a tool called OHUA, OHUA, which was a language that...
Tell me more about this.
So
I didn't hear the name.
I only read a bit of the thesis, but it was a language that compiles down imperative code into Dataflow graphs. It was designed for parallel same machine execution, not distributed, but it might be interesting and worth looking into. Yes,
please. I would like to hear about it. Let me tell you what we found. By asking people, we got to two things. One is I visited one is that people tried basically to take imperative code and execute it in GPUs. And in order for them to execute it in GPUs, they did have to transform it to the Dataflow graph. But that was not for transactional applications and, state sensitive, but basically analytics. The other thing is that I visited the folks over at KTH roughly 2 weeks ago. And in fact, I think I have seen Jonas here. Yeah, Jonas is here. And basically, let me see. So basically, Philip Haller mentioned that for Scala async, he has done a very, very similar program analysis, similar to the function splitting we are doing here. So whenever you had, for example, async, go do something, and then on the await, you would have to basically block and do something else. He said that this made it to the actual compiler of Scala eventually. He did not compile it to the Dataflow graph. But again, the type of program analysis is extremely similar to what we are doing here. He also mentioned that he never wrote about it, which to me sounds quite funny. I was discussing with Elko Fischer before he died, basically, last year. And he did not have a name for this type of analysis. He had the name for continuation parsing style and what we transform it into before we get to the data flows, but he did not have a name for this type of analysis that happens before we get to the continuation parsing style. If anybody knows those names, we would also be very interested in hearing about them. What most people have been doing, according to Guido Salvaneschi, what most people have been doing in PL traditionally is to take functional programs and compile them to imperative programs, but nobody wanted to take imperative programs and compile them into functional programs, and as a result to Dataflow programs, which to me is extremely impressive. If that is the case, I find it impressive. Anyway,
Okay,
because I thought we were doing standard PL things, if you ask me, and actually not really.
Cool. I think it's time for the morning tea break and coffee break. So thank you very much, and we'll be back.
Thank you.
Thanks everyone for the discussion, and thank us again for being here.